at this example of a related rate problem. In this one, a streetlight is on top of an 8-foot pole. Joe, who is 4 feet tall, walks away from the pole at a rate of 2 feet per second. At what speed is the tip of Joe's shadow moving away from the base of the pole when he is 13 feet from the pole? If you've seen an example where the question is asked, what rate is the length of the shadow moving, that's different than this one. This is the rate of change of the tip of Joe's shadow from the base of the pole. All right, so just like before, let's draw a picture first. So we have a street light sitting up here. We'll even give it some color. My street light's going to be pink. Fun. And we have in this, and let's remember, label things that do not change and that are fixed. And so this pole, which is 8 feet tall, will never be anything other than that. Joe, who is 4 feet tall, so he's half as tall as the pole. I'm going to label that as 4. Walks away from the pole at a rate of 2 feet per second. So he's going this way, walking away. And so this right here is a distance that's changing. So I'm going to label it as X. All right. At what speed is the tip of Joe's shadow? So the shadow is coming down, or is created by the light hitting the back of him and casting this shadow right here. Okay? So if I extend this line this way, we may be tempted to think that this is the distance that we're talking about, but that's the length of the shadow. When we say we want the tip of the shadow from the base of the pole, then we mean this distance right here. And it's changing, so we're going to label it as Y. All right? Perfect. Now, let's list other information that we're given, and that is that he walks away from the pole at a rate of 2 feet per second. So that tells us right here that dx dt is 2. Now, it's positive because this distance is getting larger. Great. And we are looking for dy dt. I like to clearly identify what it is I'm looking for. Dy dt. All right, and now we want to find a relationship with what we know and what we're looking for. And so we have a triangle. We may be tempted to think of Pythagorean's theorem, but this time I believe what we want is similar triangles. And so remember, with similar triangles, the ratio of the lengths of their sides is equal. So this distance is to this distance, so our super triangle, 8 is to y, let's scoot that up, as 4 is to this distance. And you got to be careful here. How do we talk about this distance in terms of our x and y? Well, it's actually y take away x. So as 4 is to y minus x. Okay, so the hardest part is done. We have identified all of our pieces, and we have found a relationship between what we know and what we're looking for. So our next step is to apply the calculus and take the derivative of both sides with respect to t. However, before I do that, I am going to simplify by first getting rid of this fraction. So I can write this as 8 times y minus x equals 4y. And I can even go further and group all my y's on one side and my x's on the other. So this is 8y minus 8x equals 4y, or 4y equals 8x. Or y equals 2x. All right, so I've simplified my relationship as far as possible, so I'm ready to take the derivative of both sides with respect to t. So y equals 2x, take the derivative with respect to t, we get dy dt equals 2 times dx dt. Now, remember, I came back here to circle what it was I was looking for. So that reminds me of where I'm going in the end. So now I'm at the point where I'm ready to plug values in, and I see that I can plug in dx dt as 2, which means dy dt is 4 feet per second. It's positive because this distance is growing as the man walks away from the pole.